1 connected to 2 to 3 to 4 and 5. So this is the least folded version. So this is the maximum folded version. Okay? So we want to quantify, given an arbitrary graph, how much folded it is, or an arbitrary protein. Okay? How much folded the protein is. Okay? So clear. So again, the idea of quantifying to have a feel of some property. Okay. So the way we'll do that is we'll again run through the eigenvalues program and find the eigenvalues for each for a given graph. So this is for this graph of 5 vertices, you're going to have 5 eigenvalues. So find e to the power of those eigenvalues. You know what is e to the power, right? The exponential sign in your calculator. So find e to the power of negative 1.618, you will get 0.2. E to the power of negative 1.473, you will get 0.23 and so on. So obviously, the larger the value, more positive it is, the larger the e to the power. Okay? So e to the power 2.935 is 18.65. So you can see here, it really dominates over the other values that you got. Is that clear? So more positive and larger the eigenvalues you're going to have, the larger e to the power. Okay? So then what you do is just sum this all these e to the power values. Okay? So that is this 21.56 for this example. So once you do that, again this 21.56 may not give you okay how much is the folding there. You don't get an idea right away by looking at that number, right? So one way to do to make it more meaningful is, so this is the graph that we looked at is a graph of 5 vertices. So if all those 5 vertices are connected to each other, it will become a complete graph like this. So run through the eigenvalues program again for this such a graph. You will get the eigenvalues to be like this. One eigenvalue is very large, like 4. Probably there are 5 vertices, so 1 less than that, 4. And the other eigenvalues are negative 1. Okay, so that this is like a property of the complete graph. So you can try a complete graph of 7 vertices and see what eigenvalues you get. Okay, or likely you will get all negative ones and the other will be 6. Okay, so now try to find e to the power of those eigenvalues. So again, the one with the positive eigenvalue has a very large contribution compared to the others. So the sum is 56.048. So for this arbitrary graph that we just saw before this, the sum of all the eigenvalues was like what? 21 point something, right? So divide this by this sum of all the e to the power values for a complete graph. So this ratio is going to be from 0 to 1. Because the complete graph is going to have the largest value for this sum. Okay. Now the name for this is called Estrada index, the sum of all the e to the power of eigenvalues. So you take the ratio of the Estrada index you got for the given graph to that of the Estrada index for the complete graph. Okay. So that ratio will give you an idea how close is the given graph from being a complete graph. Like the previous case, you analyze how close is the graph from being bipartite. So here you are analyzing how close is the graph from being complete graph, or in the context of a protein analysis, how close is the network, the protein network is from being what? Folded, completely folded.
How we will know that the protein is like more completely like packed?
Yeah, so look at the amino acids. So these are the amino acids.
Okay, all nodes are.
All nodes are the amino acids are modeled as nodes, and if there's a bonding between two amino acids, there's an edge between them. Okay. So if you look at the amino acid chain like a chain 1, 2, 3, 4, 5. Their Estrada index comes out to be very small, relatively small. So these are the eigenvalues, e to the power of eigenvalues. Sum of them is 9.88 for a chain like this. So 9.88 is smaller than 21 point something that we got for a graph that is more folded than a chain. Okay, so again the ratio of 9.88 divided by 56 is going to be smaller than the ratio that we got for the other graph. Okay, so that's the approach. So if you want to find the folding index, the folding effectiveness, find the Estrada index, which is the sum of all the e to the power of eigenvalues for the given graph, and just based on the number of vertices that are there in the given graph, like in this case all the graph I show here have 5 vertices, find the Estrada index for a complete graph of those 5 vertices and take the ratio, and we can call that as the folding effectiveness. So if it is 1 or close to 1, it's an indication that the protein has completely folded.
Sir, I know the numerator value, but what is the denominator value? What is the denominator value?
Denominator is the for a complete graph, Estrada index for a complete graph. Remember I just showed you that complete graph, that every vertex is connected to every other vertex. Okay, so just repeat the process for this complete graph. You'll get all the 5 eigenvalues for this complete graph, and find e to the power of them and sum them up. That will be the largest sum. Okay, so if you are given an arbitrary graph, right, we will go through the approach of finding its eigenvalues, e to the power of eigenvalues, and so on, and find the sum. Now, just find out the number of vertices in the graph. So that graph has 5 vertices. So this is a complete graph of 5 vertices. So write down the adjacency list and find the eigenvalues, and find e to the power of those eigenvalues. Sum them up. That's all. So for the original given graph, you got say 21 point sum as the sum. That's called the Estrada index. The sum of all the e to the power is called the Estrada index. So the Estrada index for the given graph was 21 point something, and for a complete graph with the same number of vertices, you got 56.
The Estrada index for given graph, it's already given the value will always.
You have to find it out. What will be given is just the graph. So given the graph, you can find its eigenvalues, right? So let us say you're given that graph. You can find its eigenvalues. You can find the Estrada index, which is sum of all the e to the power of eigenvalues. It comes out to be 21.56. Is that clear? So now what you do, just, you see there are 5 vertices. So draw a complete graph of 5 vertices. Write down the adjacency list, run through the program, find its eigenvalues and the e to the power of eigenvalues. Sum them up. So that's the Estrada index for this complete graph. So now you've got the numerator and the denominator is 21.56 for the given graph and 56.048 for the complete graph with the same number of vertices.
Means I'm getting confused that the given graph and between complete.
Complete graph is something you can generate, right? When you once you know the number of vertices. What is a complete graph? Every vertex is connected to every other vertex.
Means okay, we need to create like we need to connect every.
Every vertex to every other vertex. So if I give you a graph of 7 vertices, you don't need to even draw a complete graph of 7 vertices. You can know the edges are going to be like 1, 2, 1, 3, 1, 4, like 1, 7, then 2, 3, 2, 4, 2, 7, 3, 4, 3, 5, you see. You can type all the edges like this and feed to the program. It will give you the 7 eigenvalues. So that's it. So I'll give you only the graph. You have to find the numerator and the denominator. See, the denominator is always the same for a graph of 5 vertices because it's for a complete graph.
Oh, okay, yeah.
It's a numerator that will change.
Yeah.
Is that clear now? Anybody else has any question? So the more you go as a chain, so this is more complete or folded. This is relatively less folded because look at the ratio. folded. Okay? And if you go as a chain, it's going to be even less. Okay? Alright, so now we will go on to connectivity. So this is another application. How to quantify how connected a graph is. When we did breadth first search, we found out that when we run breadth first search, we can reach all the vertices. We can say all the vertices are in one partition, right? Remember that? So if you run breadth first search and we cannot reach all the vertices, we can reach only few vertices, then all those vertices that are reachable are considered to be in one partition or component. So this graph of 7 vertices, 1, 2, 3, 4, 5, 6, 7 is not connected. Connected means they are not reachable from each other. So you can say these 4 vertices are in one component and these 3 vertices are in another component. Okay. Now if there's an edge between them, then it kind of bridges the 2 components. Okay. So such an edge that if you remove from the graph, if the graph gets disconnected into 2 or more components, it's called a bridge. Okay? Whereas if I remove, say, this edge, the graph is not going to get disconnected. So that edge is not a bridge. Okay? So we want to now again quantify, given a graph, how connected a graph is. Because if I remove any arbitrary edge, would the graph get disconnected? Then the graph is not very strongly connected, right? But it's only few edges that if you remove will make the graph disconnected, then the graph is more strongly connected. So if you look at these 2 graphs, right? Which graph you think is more strongly connected?
The second one.
The second one, right? Not just because it has more edges, but you can see here this edge
Connectivity also high.
is increasing the connectivity because yeah, so that's the only difference between these 2 graphs, right? This edge, isn't it? So we could now again quantify how much it increases the connectivity, the presence of that edge on relative basis. So we could determine something called the algebraic connectivity for each graph, for any graph. And if you determine the algebraic connectivity of this graph and the algebraic connectivity of this graph, it turns out that from 1.108, the connectivity increases to 1.382 just because this edge is there. So that is a kind of field that we want to get, how much the connectivity of a graph is. And if you want to just remove an edge and reassess the connectivity, the algebraic connectivity, we can find out, okay, this edge is so important for the graph. Is that clear? Okay, so that's what we're going to do. So we're going to determine what is called the algebraic connectivity for a given graph. So to determine that, see the previous 2 applications or even before that last class, we just feed in what? The adjacency matrix or the adjacency list to your eigenvector program, right? I said there's one application or probably later one more for which you cannot use the adjacency list as an input to a program. You have to use the adjacency matrix version of the eigenvector program I gave you. And this is that application. So why? Because you're going to determine what is called the Laplacian matrix for a given graph and feed that as input to your eigenvector program. Okay? So how to find the Laplacian matrix? So it's very simple. It's a square. It has the same number of rows and columns as the number of vertices. So this has 5 vertices. So you have 5 rows and 5 columns. The diagonal is nothing but the degree of the vertices. So this is like for vertices 1, 2, 3, 4, 5. This graph. So you see here the mathematical representation. If I equals j, which means the row index equals column index, which means the diagonal, then the entries represent the degree of that vertex. So the degree of 1 is 3, the degree of 2 is also 3,